Alright, this is the second video on 5.6, which is covering the ratio and root tests. This video will specifically cover the root test. So the root test, given the series, the sum n equals 1 to infinity of a sub n, let the limit as n goes to infinity of the nth root of the absolute value of a sub n equal rho. If 0 is less than or equal to rho, which is less than 1, then the sum n equals 1 to infinity of a sub n converges absolutely. If rho is greater than 1 or rho is equal to infinity, then the sum n equals 1 to infinity diverges. If rho is equal to 1, then the test does not provide any information. So we got to try a different test. So before we jump into some examples, let's go ahead and get a helpful result. We're going to show that the limit as n goes to infinity of the nth root of n is equal to 1. So the limit as n goes to infinity of, and the nth root is the same thing as the 1 over n power, we're going to go ahead and assume that that's equal to y. We're going to go ahead and apply the natural log of both sides. And then using the continuity of the natural log, we're going to slide the natural log past the limit. And so the natural log of n to the 1 over n is going to be equal to 1 over n, natural log of n, which can also be written as the natural log of n over n. Okay, and that's going to be equal to the natural log of y. Well, you do have a form of infinity over infinity right here, so this is infinity over infinity, and so we can apply L'Hopital's rule. So this becomes the limit as n goes to infinity. The derivative of natural log of n is 1 over n, and the derivative of the n in the denominator is 1. Okay, and that limit is going to be 0. So, as n goes to infinity, y must go to 1 because the natural log of 1 is going to be 0. So, the limit as n goes to infinity of the nth root of n is equal to 1. Okay. In the next two examples, we're going to pick on the P series 1 over n and 1 over n squared again. So the sum n equals 1 to infinity of 1 over n, that is the divergent P series, the harmonic series where P is equal to 1. We're going to try to apply the ratio test, we're going to try to apply the root test to it. So the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to the limit as n goes to infinity of the nth root of 1 over n. Okay, so then the limit, this is going to be equal to the limit as n goes to infinity, and the nth root of 1 is 1, and we have the nth root of n on the denominator. We just showed that the limit as n goes to infinity of the nth root of n is equal to 1. So this is equal to 1 over 1, which is 1. And because that limit is 1, the root test is inconclusive. Okay. And because the root test is inconclusive, if we're trying to figure out if this converges or diverges, we have to use another test. And so we already know that it's a divergent P series, P equals 1, which is less than or equal to 1. Now we're going to take a look at the sum n equals 1 to infinity of 1 over n squared, and we're going to try to do the root test on this also. So the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to the limit as n goes to infinity of the nth root of 1 over n squared. That's going to be equal to the limit as n goes to infinity. The nth root of 1 is 1, okay? And then the nth root of n squared, we can write that as the nth root of n quantity squared, and that's using properties of exponents. So the nth root of n as n goes to infinity is going to be 1. So this is going to be equal to 1 over 1 squared, or just simply 1. And again, the root test is inconclusive. Okay. However, we know that this is a convergent P series, where P is equal to 2, and that's greater than 1. All right. So this is an example of why the root test is inconclusive if the limit of the nth root of the absolute value of a sub n is equal to 1. The series could either diverge or converge, and that's not a good, that just doesn't give us a good result. We got to try something else. So root test is not going to work on P series, so you're going to want to use the P series test. We got a couple more examples to go through and work out applying the root test. Typically, you want to use a root test when you're involved with like an nth power, and then probably you want to stay away from factorials if you're trying to use the root test. All right, so we're going to look at the sum n equals 1 to infinity of 1 over n to the nth power. So the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to the limit as n goes to infinity of the nth root of 1 over n to the n. This is equal to the limit as n goes to infinity. The nth root of 1 is 1, and the nth root of n to the nth power, the nth root and the nth power will undo each other. And so we just have 1 over n, and the limit as n goes to infinity of 1 over n is equal to 0. Okay, and that is less than 1. And so if the limit is of the nth root of the absolute value of a sub n is less than 1, then the root test says this converges absolutely by the root test. Okay, we're going to look at two more examples. We're going to look at the sum n equals 1 to infinity of 9n plus 12 over 8n plus 11 raised to the nth power, and we see that nth power, so we're probably going to think the root test is going to be the best bet to figure out whether this series converges or diverges. So the limit as n goes to infinity of the nth root of the absolute value of a sub n, that's going to be equal to the limit as n goes to infinity of the nth root of 9 plus 12 divided by 8n plus 11. And that's all raised to the nth power. So we have the nth root and the nth power. They are going to undo each other. And so we're going to be looking at the limit as n goes to infinity of 9n plus 12 over 8n plus 11. Now this is just a horizontal asymptote here, or if you want to, you could use L'Hopital's rule or factor out the highest power of n, but this limit is going to be 9 over 8. 9 over 8 is greater than 1, and so the root test says that this is divergent. Okay. All right, we got one more example here. We're going to look at the sum n equals 1 to infinity of 5e to the 10n divided by n to the 11n. And this is actually a series fairly similar to the last example we looked at in the alternating series test. And so I think that's going to be the last example on the third video for alternating series, the part 3. Now, this is not exactly the same series. This is not an alternating series. We could easily throw an alternator on there, not a problem at all. But I had mentioned in that video that series, if we wanted to show absolute convergence, we would want to use the root test. So this would be very similar. The absolute value, so we have limit as n goes to infinity of the nth root of the absolute value. The absolute value would knock out the negative 1 to the n. And so we'd use that for that particular problem to show absolute convergence. So anyways, let's go ahead and take a look here. This is going to be equal to the limit as n goes to infinity of the nth root of 5 e to the 10n over n to the 11n. So this is going to be equal to the limit as n goes to infinity. And we can go ahead and apply properties of roots here. So the nth root of a times b is equal to the nth root of a times the nth root of b. So we're going to go ahead and apply that to the 5 and to the e to the 10n. So that'd be nth root of 5, and then the nth root of, so I skipped a little bit of a step there, so the nth root of e to the 10n, okay, is the same thing as the nth root of e to the 10th, and then raise, oops, no, that's backwards, to the nth power and then to the 10th. And so you're left with e to the 10th power. And then we also use the property, the nth root of a over b is equal to the nth root of a over the nth root of b. And so the nth root of n to the 11 n is equal to n to the nth root of that, and then raised to the 11th power, and so that gives us n to the 11th. Okay, and you got, so the nth root of 5 earlier, that would be the limit as n goes to infinity of the nth root of r. That's going to be 1. So the top is going to go to essentially 1 times e to the 10th, and then the bottom is exploding to infinity, and so that limit is going to be 0. That's less than 1. And so the root test says that this converges absolutely. Okay, and again, the last example in part 3 of the alternating series had a problem similar like this. We didn't show absolute convergence because we needed the ratio test. We just showed conditional convergence by the alternating series test. That can be that problem can be you can show it converged absolutely, just like what we did here. Okay, so converges absolutely by the root test. Okay. All right, that's it for this video. We'll be jumping into Chapter 6 soon, so we'll see you next time.